So, I'm very pleased to introduce Professor Sigrid Angenent from the University of Wisconsin. And he will talk about the zoo of solitons.
Well, thank you, Susanna and Brett, for inviting me here. So I'm going to talk about the solitons that show up in curve shortening. Solitons are special solutions to curve shortening, and I'm going to spend, since it's a general talk, I'll spend some time explaining what curve shortening is and reminding you of some of the older results from the late 80s. And then I'll get on to the special solutions that I've been looking at. Everything I'm talking about is joint work with Dylan and Steve Altschuler and at Texas. So let me begin with just a reminder of what curvature is. The whole talk will be about curves. So for a plane curve, curvature is essentially the following. Here's a plane curve. You pick a point, and at a point you draw the tangent angle. And as you move along the curve, this tangent will rotate. And so this angle, if you call that theta, then the curvature is just the derivative. It's the rate at which that angle changes as you move along the curve. So different version of describing that is instead of looking at the tangent angle, you can at each point of the curve draw the tangent vector. And now there are two. So this is the unit tangent vector. There are two unit tangents. So when I draw one, it implies a choice of orientation along the curve. And so with a unit tangent, we can also draw a unit normal. That's a vector perpendicular to it. And so the unit tangent and unit normal. So these are vectors, and sometimes I will write arrows on top of vectors, and sometimes I'll forget that. T and n are always a right-handed basis, so turning from t to n is always counterclockwise. And the curvature satisfies, the different way of defining the curvature is to say that the derivative of the unit tangent with respect to arc length, as you move along the curve, this vector rotates, and the rate at which it rotates is exactly the curvature. So now if you differentiate this thing, this vector, it will rotate in that direction, so the derivative of t will be perpendicular to t. It's a unit vector, so it will be a multiple of the normal. So this will be k times n. And then there's a second formula which I will not use, but if you start doing calculations, it's useful to know. The derivative of the unit normal is minus the curvature times the unit tangent. So this is essentially what the curvature is for plane curves. For space curves, first three-dimensional space, I'm heading. So here's a space curve. So you can essentially draw the same thing. You can have a space curve. Like, let's say here I have a helix. You can do the same thing. At each point, you can draw the unit tangent. And as you, so now I can't draw a unit normal because perpendicular, it would have to be a unit vector that is perpendicular to this tangent vector, but there are many of those, so I would have to make a choice. There's no obvious choice, at least at first sight. But what you can say is that the derivative of t with respect to s, this has to be a vector that is perpendicular to t, just because t is a unit vector. And so you can just define that to be the curvature times the normal. So as long as this derivative is non-zero, this unit normal is well defined, so that gives you a second vector. So all this is familiar from what this is. Third semester calculus. Okay, so you get unit tangent is in that direction as the curve. As you move along the curve, it rotates. Its first derivative is a multiple of some vector perpendicular to t, so that vector we call unit normal. In this case, the assumption is always that k is positive. Otherwise, so assuming that k is positive fixes which of the two ends you choose. And then there's this third vector. If you just complete this to a right-handed orthonormal basis, then this third vector that is called the binormal. So I will never use the normal and the binormal here. The basic formula that I'm going to use is this one. The curvature of the curve is the derivative of the unit tangent. It's the curvature times the unit normal. That formula works in 2 dimensions, in 3 dimensions, and in higher dimensions you get the same thing. If you have a curve in Rn, then you can define this so. If x is a curve in Rn, so it's a function from R to Rn, then let's assume that it's arc-length parameterization. This means that dx ds is a unit vector. And then you can define the curvature of this state, k times n. You can define that to be the derivative of t with respect to s. And since t is the derivative of x with respect to s, that's a second derivative of x with respect to s squared. Okay, so that's the definition of curvature. So for most of the talk will be about space curves, but I'll also talk a lot about plane curves. So these first two definitions are the important ones. So curve shortening is a purely geometric problem. It's a problem in which we have curves and we let them evolve, we let them move, so there's an extra variable time. And we're going to describe a difference equation for how these things move. So let's talk about moving curves or evolving curves. Right? Evolving curves. Here's a curve at a particular time, and let's say it moves, and a little later it's here. And let's say we have a parameterization, x is x of t, and then we have a parameter which also called c along the curve. Then what is the rate, what is the velocity of the curve? Well, what you do is you fix the parameter c, and this is the parameter along the curve, and then you can differentiate with respect to t. So dx dt that's the velocity of the curve. And in this picture, so in the picture it would always be if you fix the parameter c, then as t changes, you know that this point will move from this curve to the next curve, to the next curve, and so on. And so this velocity itself is not a geometrically good quantity. The quantity that we care about is the normal component. So the important component that we look at is okay, so that's the normal velocity. And so this is the, so for instance here, I took this point on the curve, I keep the parameter value c fixed, I let the curve move, then as the curve moves, this point traces out, it stays on the curve as it moves along. It moves in that direction, and the normal component of the velocity vector would be this. So what I have to do to calculate that is at each point I have to subtract. So to go from this vector to that vector, I have to subtract this. Here I have to subtract that. I have to subtract a multiple of the tangent vector. Okay, so in a formula, so I'm not going to write partial derivatives like this all the time. I'll abbreviate dx dt is x subscript t, so I'll use this notation for partial derivatives. So xt perpendicular it's just xt plus some multiple, some lambda times the unit tangent, where this is chosen so that this is perpendicular to, so that this whole quantity is perpendicular to the unit tangent. Okay, so the way to calculate that is you take the inner product of this thing with the unit tangent. This has to be 0. It's a unit vector. This is 1, so therefore lambda is minus t of x. That construction is going to show up a lot. So I have a special notation for this. Let me put that here. So the projection along t, or thermal projection along t, of some vector a is just a minus that inner product times t. So that means that the normal velocity is the projection along the unit vector of xt. Okay, so what is curve shortening? Curve shortening is the following. We're going to allow curves to move in the direction of their curvature vector. I'm going to look at curves that evolve in such a way that their velocity, or at least the normal component of the velocity at each moment and any point on the curve is equal to exactly their curvature vector. So this is x, s, s. So this is the second derivative with respect to s, that's this thing. And so this is a partial differential equation, and if you write it out in coordinates, so there's a lot to be said here. If I do that, then I'll run over time in a very bad way. But so if the curve is the graph of a function, y is f of x and t, like this. So this height is f. Then you can take all these formulas and do some basically calculus with them, and it turns out that this, so for graphs, is equivalent with saying that the partial derivative with respect to time of this function, so the height, its time derivative, has to be equal to the second x derivative it has to be essentially this. So it has to be this combination. And if the curve is not a wavy graph like this, but if it is something that is, if it's a very flat curve, so it's close to horizontal, so in other words, if the x derivative, the f dx, if that is small, if you could neglect this, if that's small, then you can say that this is roughly the second derivative of f with respect to x, and the equation that you showed that you see here is one of the three standard PDEs that you see in every introduction to PDEs. It's called the heat equation. So if you ignore this part, it's an extremely well studied partial differential equation. And so there are formulas for solutions. It's known that if you prescribe an initial curve, then there exists a solution in forward time, but most of the time not in backwards time. It has all kinds of properties. Okay, so this is useful if you're going to do a lot of analysis on this. I won't be using anything about partial differential equations for the rest of the hour. Let me go to examples of solutions. So examples of solutions. The simplest example, well, the simplest example is a straight line. So I put a straight line has curvature 0. If you just let it sit still, its velocity is 0. That's a solution. 0 is 0. So a straight line is a steady state. It's an equilibrium solution. It's a solution that doesn't move. So not an interesting solution. If you take a circle with radius r, then what is the curvature of that circle? It is so the curvature of this circle is 1 over r. So I'll let you do the calculation. It's the radius of curvature. The radius of curvature is r. Its curvature is 1 over r. What is the normal velocity? So the normal velocity, and now I should have said I have to write, let me draw the vectors. So the unit tangent is this. The unit normal is this. So if the curvature is 1 over r, then the curvature times the normal is 1 over r times the normal vector. And dx dt, if I parameterize this thing, if I just parameterize it by the angle at all times, then dx dt will actually be a radial vector. So it's going to be dr dt times the unit normal. And there is something wrong here. It's minus this. Why is it minus that? If the x dt is a positive multiple of n, that means that this point is moving outwards. And my unit normal is pointing inwards. So this is dx dt, then this thing is a negative multiple of n. That's why I have a minus sign here. Okay, these two things have to be equal. So for curve shortening, these two things have to be equal, or at least the normal component of this thing has to be equal to that, but this thing is already perpendicular to the curve. So those two things have to be equal, so what you find is that for the circle, curve shortening just says, it says dr dt is equal to minus 1 over r. Multiply both sides with r, you find r dr dt is minus 1. The derivative of r squared is equal to minus 2. And therefore r squared goes to 0 linearly. And so this is a simple differential equation, ordinary differential equation. The radius of the circle is the square root. Now there's an integration constant. If you put it in, it's nice to call that integration constant. Well, if you put it in, it goes like this. And so unfortunately this t shows up. That's not t. That's the integration constant. That's not the unit tangent. Okay, so that's the integration constant. That's the time at which. So what does a circle do? It just shrinks and shrinks to a point, and at some point it just reaches its center, and after that there is no solution. Okay, so this capital T is the time at which the circle the solution disappears. A nicer way to write this equation is to say this. The rate at which so I just multiplied the equation by pi. The rate at which pi r squared is the enclosed area of the circle. The rate at which the enclosed area decreases is minus 2 pi. So that turns out to be true not just for circles, but for any curve. So let me just draw this for convex curves rather than for, so I'm drawing a convex curve. What I'm saying is actually true for non-convex curves, but the drawing becomes messier. So here's a curve, and here, by curve shortening, it will shrink. It's convex, so the curvature is always pointing inwards, so this thing will move inwards. How fast does the enclosed area increase? If you have a curve that is moving inwards, then the rate at which the area changes is, well, it's an integral along the curve. So if I take a small piece here of the curve, and so let's say this piece has length ds, then the area that gets swept out by this thing is roughly a rectangle, and that rectangle is, so it has width ds, and this side is the velocity times the amount of time that we allow to go by. The velocity is the same as the curvature. So in arguing like that, so following this argument, it's if you integrate the velocity along the curve with respect to arc length, that's the rate at which the area gets eaten up. Just adding lots of those together. If I do this, then v has to be the inward velocity, and the inward velocity, this thing has, the curvature is positive. Let's see, there's one thing, there has to be a minus sign here. Okay, so if the velocity is equal to the curvature, then this is minus the integral over the whole curve of the curvature, ds. And the curvature is just the rate, is the derivative with respect to the arc length of the tangent angle. And therefore, so what is the integral of the derivative of theta? That's just the amount by which theta changes as you go around the curve. So if you go around the curve once, the tangent angle, rotates exactly once by through the whole angle of 2 pi. Okay, so this is always minus 2 pi. Okay, so this calculation that we have here is a special case of that calculation. The enclosed area always decreases by at a steady rate. So that means that, okay, so now let's start showing form of the computer. So there are general theorems by the earliest general theorems on this subject were by Gage and Hamilton, and then very soon afterwards Grayson, and this is 1986, 87 roughly. So they proved the following things. So together they proved that, so Gage and Hamilton proved that if you take a curve and it has a convex shape, then it will shrink to a point. And as it does so, it will become rounder and rounder. If you look at it, if you zoom in on the curve, you get it will converge to a circle. You can see it looks more and more like a circle. That's Gage and Hamilton. What Grayson showed is that if you take any curve, an embedded curve without self-intersections, then it always stays embedded. It never forms self-intersections. And within finite time, it will become convex. So if you take any curve, no matter how wild it is, within finite time it becomes convex and then it shrinks to a point.
Take the connector to your computer and just take it out, put it back in.
Yeah.
That should.
You should also wake up this computer. Okay, so here's an example of a solution to curve shortening. Right, so I started with this. Let me stop with, well, the initial curve that I had, how was it created? This curve, this is the initial curve. The way this thing was created was I took a unit disk, and first I just slid it, so you think of the unit disk as built of horizontal stripes, and then just slid them back and forth sideways, so that doesn't change the area. And then the resulting thing that I had, I divided it into vertical slices and slid those up and down. And then you get a very complicated curve, but the enclosed area is exactly the same as that of a unit disk, which is pi. So since the area is decreasing at a rate 2 pi, this thing should become singular in time half a second, right? Or 1/2 of the time. So down here we have the time, so at time 0.5 the thing has to vanish. Before that happens, according to Nat Grayson, this thing has to become a convex curve. Right, and you see that the initial evolution is very quickly. All the high curvature things are moving quickly because high curvature means high velocity. So those things disappear quickly, and then suddenly now it's become convex. And now, according to Gage and Hamilton, if you look at this thing long enough, it should become rounder and rounder and shrink to something that looks like a circle. Okay, so there it goes. So that's one. This one. So let me show this. So is this this is not an embedded curve, right? This thing has, or it has a self-intersection. So there are various interpretations of how this thing would evolve under curve shortening. What are we seeing here? Is this a figure 8 that has a self-intersection, or is this is it a curve? If you just take the outer rim, is it a curve that comes here, has a dent, and then goes back like this, and then goes around and has another dent here, and it goes around like this? Or are these two curves that just happen to touch each other? So all those interpretations could give you different evolutions of curve shortening. So there's a uniqueness problem. So here are the three evolutions that you can get. So the inner ones are what you get. So I look at the time at which the inner ones disappear. That was roughly time 0.22. And the outer one had twice the initial area because it enclosed both initial regions, so it should take twice as long to disappear. So that's roughly right. So okay, so the what I wanted to talk about is what are self-similar. So generalizations of the circle. There are. Switch on the light just for a second. So let me just briefly talk about self-similar solutions here. The circle is an example of a self-similar solution. It starts out being a circle, and as it evolves, it doesn't change its shape. It stays a circle. The only thing that happens to it is that it changes its scale. So it evolves by dilation. Right, it shrinks. There is another curve, and so this is. So now you can ask, are there other curves that evolve by dilation? And so in the plane, the answer was found by, again, in the late 80s by Abrich and Langer. And so they look like this. So there are closed curves. Right? This is the simplest one that they found. It's sort of a rounded pentacle, a rounded pentagram. And so there are more complicated ones that I won't try to draw. And then there are ones that do this, but they don't close up. And so they do something like this. And they never actually close up, but these are curves that if you let them evolve by curve shortening, they will do the same thing as the circle. They don't change their shape, they just they shrink to the origin at a particular time. Yeah, let me talk about how long it takes. So these are the curves that you find that translate, that evolve by dilation. So other things that you can think of, so instead of dilating, you could ask, are there solutions that evolve by translation? And there exists in the plane there is exactly one kind of curve, and it's the graph of minus log of cosine x. And so this curve evolves by, actually if I put plus t here, now it's a function of two variables. So what does this thing do? It's this shape, and as time varies, it just translates upwards with a constant velocity. Okay, and this thing was long known, and so in the 80s, Altshuler and Grayson wrote a couple of papers about space curves, and they invented names, so they called this thing the Grim Reaper. And I think the reason is that you can use the maximum principle to, as this thing moves upwards, because of the maximum principle, anything that lives here has to disappear by the time this curve slides past it. So you can prove it use it to prove that certain things disappear in solutions to curves where you disappear within a certain time. So there exist translating solutions, and all these self-similar solutions, they're called solitons. The other thing that you could look for is, are there rotating solutions? So let me. So there exists a curve, or a whole family of curves that look like this. So they call this the yin-yang solution. So if you look at what the curvature of this curve does, this part wants to move in that direction. It's curved in that way. This part wants to move in that direction. This part has no curvature, so it just sits still. It's an inflection point. These things want to move in, but very slowly, because they have very slow curvature. So these outer spiral arms are moving in very, very slowly, but they do it in the same, but they're also bent outwards a little bit. So the net effect is that if you take this curve as initial condition, what it will do is it will just rotate at a constant velocity. Okay, so that's a rotating solution, and now you can ask: are there you can ask, do these things exist in higher dimensions? And can we come up with solutions that do perhaps combinations of these things, things that rotate and translate, or things that rotate and dilate at the same time, or dilate and translate? So that's, so for space curves, how would this work for space curves? We can, so there are three, which one in the middle. are there solutions to curve shortening that evolve under space curves that evolve by rotation? So here I would look for solutions, so for rotation I would look for solutions that are parameterized by x at time t is equal to, and now I want this to be a rotation of x at time 0. So that x star would be a fixed curve. And so how do I implement a rotation? We just take a 3×3 rotation matrix. And, I'll write it like this. It's e to the ta, where a is 0, omega, minus omega, 0, 0, 0, 0. Some antisymmetric matrix. It's an infinitesimal rotation. So this really is just rotation. This is a rotation by an angle t around the z-axis. That's what this matrix does. Okay, so dilation, we can look for solutions that are of the form, kind of here, so that square root t minus t is going to come in, and instead of writing square root t minus t, it turns out to be better to write it as 1 minus t over some constant alpha to the power alpha over 2. Where what happens? Okay, so you, something that evolves by this will shrink to the origin at a certain time alpha. Then, so depending on the sign alpha, you get two kinds of solutions. If alpha is positive, you get solutions that shrink to a point in finite time. So this will be defined. So if alpha is positive, then this is defined for t less than alpha. If alpha is negative, then just because this is a square root, this is defined for t bigger than alpha. Okay, and x star is the initial curve. So these are dilating. These are both. So depending on the sign of alpha, you have shrinking curves or expanding curves. We'll talk about examples again later. Translation. That's the simplest to describe. That's just x at time t is just a fixed curve plus t times a vector v, where v is the velocity, right? So these things just translate by they move with constant velocity vector v. And now you can ask, are there things that do combinations? Can there be solutions that both rotate and shrink at the same time? And can you have solutions that both rotate and translate at the same time? And what would the formulas for those look like? And the answer to these questions is yes. So these things exist. You can also ask, are there solutions that both translate and dilate, but don't rotate at the same time? And the answer is they do, but they don't give you new solutions, because they give you old solutions. They give you translates of old solutions. So if you start looking for things that dilate and translate at the same time, what you will find is something that just dilates, but not around the origin, but some other point. So we won't look at those. Okay, so there's a differential equation. So which curves, how do these curves come about? I showed you the Grim-Reaper curve, I showed you these Average-Langer curves, I showed you the Yin-Yang curve. All those things are, those are particular curves that if you take them as initial data for initial curve shortening evolved by a combination of translating, rotating, and dilating. all those curves are solutions to the soliton equation, and so I'll write that down what it is. So this is an equation for that curve x star, this thing, the particular profile that shows up in each of these things. It's the curve at time t is 0. That curve has to satisfy the following. Its second derivative, so this is the curvature vector of the curve. Right, so this was k times the unit normal. The unit normal of that thing. This is the velocity with which it will evolve under curve shortening. That has to be alpha times x plus a times x plus v. And now this may not be. This is perpendicular to it, so. Right, this term makes the curve dilate by a factor alpha. So if alpha is positive, the curve will expand, and if alpha is negative, the curve will shrink. This A is that rotation matrix over there, so it tells you this thing causes it to rotate. The rotation rate around the z-axis is omega, and this vector v, that's the translation. Translation velocity v is 0, 0, and v is the velocity, the vertical. This thing will translate in the vertical direction, so that's a parameter that we can choose. And so this is not the whole differential equation. We have to add an extra term, or we have to take the perpendicular component, the normal component, because this is not perpendicular to the curve normal. Whereas this is. This is, yeah?
Does it have to translate in the direction of the axis of rotation, or is that just an assumption?
So you could make no assumptions about alpha, a, and b at all, and you would get solutions that evolve that are solitons for curve shortening, but you would find that by doing it by translating, you can arrange that this thing. By translating, basically by substituting x is some constant vector plus y, where y is your new soliton. By substituting this in here, you can kill off any component of this that is perpendicular to that's not in the kernel of A. And if alpha is non-zero, then you can kill off the thing entirely. So if you have a dilating soliton, if this alpha is non-zero, if the thing is expanding or shrinking, then just by relocating the origin, you can get rid of this term. So that's why we don't look at dilating and translating solitons. And if you have rotating solitons and you include translation but no dilation, then you can still get rid of the term, the component of B that is in the range of H, perpendicular to the curve. So in this case, it's along the z-axis. You can arrange that this thing is in the kernel of A, right? So in the z-axis. So these are assumptions, but these are without loss of generality assumptions.
So sorry, about what you were saying with rotations and translations, when you compose a rotation and a translation, you always get a rotation.
Well, if the rotation is around the z-axis and the translation is along the z-axis, I'll show you pictures.
But you get axes, right? For each time you get a rotation, but the axis is changing. Right?
Maybe I should show some pictures. Okay, so this is the analog of the yin-yang curve in 3 dimensions. We call it the wagon wheels. Right? but this is it's a curve, and so we can't draw the whole curve. That's why you see that the edge here, the end. So it has one end of the curve. This spiral is supposed to. You have to imagine that it just continues and fills the whole plane. This is a curve, and under curve shortening, it just keeps on rotating, right? So there's in the middle somehow the curve is slightly curved like that, and that's what makes it turn in that direction. Right? So the exact shape of this thing is such that this thing will keep on rotating. Now there's a this thing rotates and translates. So it rotates around the z-axis, but translates parallel to the z-axis. Right? So the composition of a rotation and a translation, if the translation is along the axis of the rotation, it's called skew rotation, I think. So this curve is a solution to that ordinary differential equation that I wrote down there. All these curves are solutions to the ordinary differential equation with different choices of parameters. So this is a rotating translating solution. We have others. Let's see. The next one would be this one translates and dilates.
Was that one on a surface of its own, or was it on some sort of a?
Yeah. So that's a good question. So for this one, no, it's not, and I think it's on the surface. It should be asymptotically like a parabola, but that's the one case that we haven't proved. So. This one here, something is a little strange with the numerics, I think. This looks very much the same as the one before, except it's not translating, it's dilating. And this thing is not exactly, but it's asymptotic to a cone. Right, so it's rotating, and as it rotates, it also expands by dilation. Okay, so this is a solution. This is an expanding solution of curve shortening. Expanding and rotating. Then we also have two solutions that shrink and rotate, and so there are many versions of those. So here's one. This one shrinks and rotates. And so it's an infinitely long curve. Most of the curve is wound up around a circle. So the circle itself is a rotating and shrinking soliton. A circle will shrink to its center, and you could say that it rotates at the same time. You wouldn't be able to see it, because if you rotate a circle, you get the same circle back again. But there are other solutions like this one that are asymptotic to that circle, and they rotate and shrink to their center. Stop this thing for a second. You'll see that the end of this curve is sort of shaped like a Grim Reaper. And here's another one. This is another one of those. This is different choices of parameters. Okay. It's the same idea, except this thing. So the difference between this solution and the other one that I showed you is that is the way it's the ratio between the dilation rate and the rotation rate. So if you change those parameters, the shapes of these curves change. And so this one lies entirely on one side of the plane, and it looks so. This circle, the asymptotic circle, sits in one plane, even though it looks like it's moving vertically. It's not doing that. An optical illusion that I hope only I have. Okay, so those are these. So there's more. Okay, so there's a whole. So here's the zoo. So Okay, so what are these? These are solutions, all these are, again, these are solitons. The top row consists of solitons that right, this thing is the yin-yang curve. This one is the wagon wheels. Now, depending on the parameters, so by changing, so there's a whole family of these things. You can take this wagon wheels, and you can there's another one of those that has where the wheels are just further apart, and you can change. There's another one where the wheels are yet further apart. You can imagine that there's a limit of these things where you just get one wheel with an infinitely long end that is asymptotic to the z-axis. And so all those are solitons that are just rotating around the z-axis at a constant rate. And then if you want these things to translate and rotate instead of just sit there and rotate.
Are there only discrete values for the...
No, it's continuous.
It's
continuous, right. So maybe before I talk about, maybe I should clarify. So if I switch this on, someone else knows how to switch it off, right? Oh, there, yeah. So this difference, let me just say something about the nature of this differential equation. So I can write this as a system of first order equations in a completely standard way. It's a second order differential equation. XS, I'll say that is, well, it's the unit tangent, so let's call that T. And then this is the derivative of XS, so this is TS. And what is taking the orthogonal component? It is, that's the projection operator that I talked about, alpha plus A. This projection, so this removes the tangential component of T. It projects along, the orthogonal projection along T. Okay, so this is a system of differential equations where X sits in X and T. X and T sit in, so for all the pictures, X sits in R3, but you can let X sit in Rn, and then A has to be some antisymmetric matrix, and B has to be a vector in the kernel of A, and alpha can be any number. So in principle, this could be in Rn, and T has to be a unit vector, so it sits in the unit sphere in Rn, in the n-1 dimensional unit sphere. Okay, so it's a system of differential equations that gives you a flow on this space. But it's a very simple system. At least to write it out, it's a very simple system of ODEs, and you can so obviously you can just put this into MATLAB, use ODE 2, 3, 4, 5, and plot the solutions. So in particular, what you find is that if you choose parameter values alpha, A, and B, if you fix those parameter values, then through any point in space, x, right, and here's the origin is here, then through any point in space, x, and any tangent, unit tangent that you draw there, there's going to be exactly one solution to this system of ODEs. And it's a very simple, this flow, it's a very well-behaved flow. The solutions exist. There's no blow up, or well, solutions could go. They can go off to infinity, but T is a unit tangent, so that can go off to infinity, and X can go off to infinity. But the velocity at which X moves is because we're parameterizing by arc length, it can't go at unit speed, so it can't go to infinity in finite time. So you have global solutions to this thing. So this. There's a global uniqueness in existence for ODEs that particularize the system. So the way these pictures were created is you just, for the upper row, you pick parameter values alpha A and B. So for the top row, there's no dilation, so alpha is 0. There's a certain rotation rate, so that matrix A is this thing with a certain value of omega, and we're not translating, so you set V equals 0. And then you take initial points and initial tangent vectors. So there are many choices that you can make, and here we've only made 4 choices. So there are many different shapes that these curves can have, right? So this is out of the sea of infinitely many possible rotating solitons. This is just this is a sample of 4. In this row, you have you have rotation, no dilation, and translation. So these things look like they are asymptotic to paraboloids. It's sort of, it's as if you took the wagon wheel and you just bent the wheels like that. Here we have solutions that don't translate but dilate. So these are shrinking, these are expanding solutions. So there V is 0, alpha is some positive number, and A is that matrix again. And again, so there are a bunch of these solutions. And the bottom row are all the, so the bottom row consists of shrinkers. So these are solutions that if you let them evolve by curve shortening, they will rotate and dilate, so shrink by dilation to the origin. So these are generalizations of the circle and of the average Langer curves to 3 dimensions. So this bottom row, I say this is a selection of all shrinking, dilating solitons. This is just, it's a sample of 4. There could be many other shapes. So the next slide shows you more of these shapes. All these are shrinking, rotating solitons. They have different, so here in each row, we're varying the initial, what are we varying here? So these are shrinking, rotating solitons, so that means that in these pictures, V is 0. We have a dilation rate alpha and a rotation rate A. And I think the thing we're changing is the dilation rate alpha. So one of the axes is the rotation rate, the other is the dilation rate. What you see here is a very small dilation and rotation rate. If you set alpha and A equal to 0, if you set A equal to 0, so this is a very small rotation rate. If you set A equal to 0, what you get is something that is, you get the equation for the average Langer curves. So those, the pentagram that I drew at the beginning. What you see, if you do that, and you take a very small rotation rate, you get a curve that is basically just a nest. It wants to be one of these spirograph average Langer curves, but there's a small term that is perturbing the thing, and it's not chaotic in the sense of dynamical systems. It's a mess. I can't say anything. If you change the parameters, you get this situation. What you see with all these curves is that they are asymptotic to a circle. They have 2 ends and they're asymptotic to a circle. All of them have, at infinity, they have, so parts that are far away from these, so parts of these curves that are far away from the origin all have this kind of shape. And if you look at this closely, so here are a bunch of solitons. There's a theorem that you can prove using that ordinary differential equations that at infinity, or if you're far away from the origin, these solitons, these solutions to this set of equations, split into 2 parts. There is, so if x is really large, this term will be large, and that means that Ts, the rate at which the unit tangent is changing, will be really large. And so if the unit tangent changes very quickly, then this will be a large vector, but it won't change very fast, because x only changes at unit speed. So that means that we can treat this more or less as a constant, and if you so if you go through all the equations, that means if you set this thing equal to a quantum constant, you get the equation for the Grim Reaper. So this means that far away from the origin, the solution has to be like a Grim Reaper. So it has to be like a little loop like that. And then the two ends of those Grim Reaper are things, are solutions, are curves for which this projection is pretty much zero. So that means, so the ends of the Grim Reaper are solutions. And so for now, let me ignore this translation, because in some cases I don't really know how to do that. So if X is large, then either Grim Reaper, in which case the unit tangent changes very quickly on a really short arc, and so that's the part. So in solutions, a bunch of these solutions, you see that that's what's in these red circles, right? It's magnified here, and then the ends of that Grim Reaper are curves on which the projection of this along the unit tangent is roughly zero. It's really small. Okay, so unit tangent. So that means that the unit tangent has to be some constant times alpha plus a times x. And now, if you allow me, the unit tangent was dx ds. And here, so this equation, so this c is just a proportionality constant. It varies from place to place along the curve. If you divide left and right, and put that thing here, and you find a new coefficient, so you do usual ODE tricks. You reparameterize x so that this becomes the integral of c becomes your new parameter. Then this just says that dx d, right? If so, the derivative of x with respect to this new parameter should be alpha plus a. Alpha plus a is a constant matrix, so you know what the solution is. X is either the zeta times alpha plus a times x times a constant, so x star. This is some constant vector. What does this look like? This is either the alpha zeta times either the zeta a. Okay, so either the alpha and zeta, that magnifies, so x star is a fixed vector, so which curve is phased out by this? Either the zeta a, what does it do? It just rotates around the z-axis by an angle zeta. Either the alpha and zeta dilates by a certain factor. Okay, so this is a solution that is, it's moving outward and it's spiraling around. It's rotating and moving out. If x star happens to be in the xy plane, or if this were a two-dimensional picture, the curve that would be traced out by this would be just a logarithmic spiral. In fact, the projection onto the xy plane of this curve is a logarithmic spiral. And it lies, so this curve lies on a cone above the xy plane, determined by the z and the x and y coordinates of x star. So that means that in the cases where there's a lot of hand waving here because I've thrown away terms and it's a formal calculation and there's no real proof that what I've said here is true, but there are proofs that this is true in some cases. It is especially for the expanding solitons. So if alpha is not equal to 0, this is you can prove lie on generalized logarithmic spirals, basically what you saw in this picture. This picture. And so all these, here alpha is not equal to 0. In this top row here, these are translating rotating things. Here V is not 0 and alpha is 0. So that's the case that I don't really want to talk about. So in this case, parts, ends of the curve that go off to infinity lie on cones. In this case, here alpha is negative. There are no ends to the curve that go off to infinity, so here there's no statement to be made. Right? This curve stays in a bounded region. It stays within this eggshell. There are no ends that go off to infinity, so we haven't said anything. What time should I stop? Am I already way over time? Okay. Yeah. Okay, so yeah, I'll stop here. If you want to see, so some of the movies, you can just Google curve shortening or Google solitons on YouTube. So some of these things are up there. So thank you.